Dominant voice speech segregation and noise reduction preprocessing module for hearing aids and speech processing applications. The objective is to design a CASA system which is capable for monaural speech separation for the design of front-end stage of digital hearing aids and speech processing systems and to reduce the computational complexity associated with the filter bank. The two major problems being faced by hearing impaired people wearing hearing aids are difficulty in understanding the speech contaminated by speech from other talkers, babble noise, and difficulty in understanding fast speech. Effective separation of one speech, that is the dominant signal from other signals, and then its amplification would be very helpful for such people. These are the outlines of the presentation: introduction to CASA, proposed model, proposed filter bank, analysis of the proposed system with the state of the art, evaluation of the proposed framework using different wavelet packets, and conclusion. Computational auditory scene analysis. Auditory scene analysis, the term referred as the ability of the human auditory system to segregate the dominant speech signal from other interfering signals. Our ability to follow one speaker in the presence of other sound. The computational auditory scene analysis is the field of study to develop the property auditory scene analysis computationally, which consists of mainly two sections, segmentation and grouping. Those are performed in frequency domain. In order to achieve that frequency, we need to achieve the frequency dispersion by means of the cochlear filter bank. The cochlear filter banks are mimic the human cochlea. The commonly used cochlear filter banks are Gameton filter bank and short-time Fourier transform filter bank. The Gameton filter bank models the cochlear filter in an effective way. However, it consists of around 128 Gameton filters, which imposes higher computational complexity to the filter bank and the segregation system, hence which is not suitable for real-time applications. Second one is the short-time Fourier transform cochlear filter bank. In order to perform the short-time Fourier transform of a particular signal, we need to choose a window. If we go for a narrow window, which will give poor frequency resolution. However, we choose a wide window, which will give better frequency resolution but poor time resolution. According to Heisenberg's uncertainty principle, there is some dilemma between the time frequency representation obtained through short-time Fourier transform. Hence, in this proposed model, we introduce a novel approach, a novel cochlear model, that is wavelet packet transform cochlear filter bank. This section consists of mainly three sections. That is, one is the modulation transform, which includes wavelet packet transform and discrete Fourier transform. Second section is the segmentation and grouping. Third section is segregation filter. We need to discuss each section in detail. These are the critical bands of human ear. We are referencing this critical band for the design of wavelet packet transform cochlear filter bank. Here I have given the demonstration of 18-channel wavelet packet transform decomposition. Here the input signal at node 00 is allowed to pass through a low-pass filter and a high-pass filter. For example, if the input signal is within the frequency range of 0 to 8 kHz, 0 to 4 kHz frequency will pass through to the node 10 and 4 to 8 will pass to the node 11. And these signals will undergo a decimation by a factor of 2 at each level of decomposition. And the process is repeated and we obtain 18 channels at the output. And these 18 output channels are represented with red color in this diagram. This is the MATLAB implementation of the proposed wavelet packet transform based cochlear filter bank, and the input signal at node 00 and the output signals at channel 1 and 18 are highlighted in this figure. We need to discuss about the first section of our proposed framework, that is the modulation transform. The modulation transform consists of wavelet packet transform and discrete Fourier transform. We have already discussed the wavelet packet transform and we have obtained the signal x of mk, which gives the relation between time and acoustic frequency. In order to obtain the frequency dispersion, we need to convert this into the frequency domain by means of discrete Fourier transform. Taking the discrete Fourier transform of the signal x of mk will obtain the signal x of ki, where k represents the acoustic frequency and I represents the modulating frequency. Once the x of ki is obtained, we can smooth the signal by allow it to pass through a low-pass filter of transfer function gs of I. We will obtain xs of ki. This signal can be again smoothed by taking its partial derivative. Once a signal is perfectly smooth, we can find the peak points from the signal and is referred as onset points and denoted with f on. In between two onset points, a valley point is identified and which is defined as offset and is marked as f off. These onset and offset points forms onset fronts and offset front member. The similar onset and offset points merges and form onset front and offset front respectively. The onset front members and offset front members possess identical characteristics, are expected to from the same source, and they are formed a group which is called group A. And the other remaining offset and onset front form group B. The group A is expected that it is represents the dominant signal and the group B is expected that is representing the interfering signal. Then we need to calculate the pitch frequency range of group A and group B to obtain the pitch frequency range of the dominant signal and the interfering signal respectively. Next, we need to move to the third section of our proposed system, that is the filter design. Here we are using a frequency mask based filter design, which is a dynamic filter, which is designed basically based on mean modulation spectral energy over the pitch frequency of the dominant and interfering signals. Here phi t represents the mean modulation spectral energy over the pitch frequency of the dominant signal and phi I represents the mean modulation spectral energy over the interfering signals. Once we have the value of phi t and phi I, we can easily compute the frequency mask ft of ki is equal to phi t of k by phi t of k plus phi I of k. Once the value of ft of ki is obtained, we can convert it as a filter by multiplying it with the phase response and taking its Fourier transform. F of m is equal to I is equal to 0 to I minus 1 f e raised to j phi of I e raised to minus j 2 pi mi by capital I. Here phi I represents the phase response, and here in this work we consider linear phase filter, hence the value of phi I will be equal to I. Once the value of f of m is defined, we can obtain the segregated signal by convoluting the filter response with the signal x of ki. These are the results obtained by the examinations using various noise such as female and male speeches, female speeches, male speeches, and other noise such as white noise, pure noise, cocktail party noise, telephone noise, siren noise, and 3 speech mixers as well. Next is the analysis of the cochlear filter banks. First one is based on the mean opinion score. The mean opinion scores measures the perceptual quality of the proposed system from the audience score. From the results, it is clear that the wavelet pocket transform possesses a better score than short-time Fourier transform. Second, in terms of signal to distortion ratio also, wavelet packet transform obtain better results in various evaluation conditions than the other techniques. In terms of time complexity, the wavelet packet transform, the time taken for the wavelet packet transform is just half that of the Gameton filter bank, and also it's very much less than short time Fourier transform. Also, we have evaluated this model in an application perspective, like we have incorporated this as a pre-processing stage of an emotion recognition system, and we have compared our proposed framework with other cochlear models like Gameton and short-time Fourier transform filter bank. And the models are evaluated in 3 distinct datasets: REVDIS, SUSAS, and ESD datasets. Ravdis and Susas are English datasets and ESD is an Arabic dataset. In all the conditions, the proposed wavelet packet transform method obtains superior results than the Gameton and short-time Fourier transform based speed segregation system. Also, the proposed model is examined with various wavelet packets such as dB4, dB6, dB10 and Haar wavelets. From the figure, it is clear that the dB4 wavelet shows an increase in the signal to distortion ratio with the increase in the dominance level. Hence, the dB4 wavelet is more suitable for a CASA system. The proposed method provides higher signal to distortion ratio, better audibility, low computational complexity. dB4 wavelet is more suitable for a CASA system. Instead of onset offset based approach for pitch estimation, correlogram based approach can be used. Thank you.